Yeah.
Can we disable cross-posting?
Okay, so hi everyone. This is ONOS Technical Steering Team meeting, and today we're going to be discussing the upcoming feature of ONOS, which will add capability to add or remove in a dynamic fashion members from ONOS cluster. And so Madan is going to present some of the base assumptions and some of the planned design, and we can open it up for questions so that we can have a discussion around that. Okay, so Madan, you can
sure. Let me share my screen. Okay. Sorry. So, hello everyone. Let's get started. And so I have when I counted, I had 26 slides. But a lot of them have pictures, so hopefully they will clarify and not confuse. But a big chunk of today's 1 hour, we want to have discussion on what works, what doesn't work, what are the limitations, and if people have comments, this is the forum. So since there's a lot of you in this meeting, and I'm not sure if everyone has the same level of understanding of what ONOS currently supports, what its capabilities are, and what the limitations are. I thought it would make sense to, level set, introduce, some of the basics, some of the principles, what we have today, how it works, what are the limitations, and then talk about the upcoming feature. So hopefully when we go through the current architecture and some of the features that we support, some of the limitations might come forward. So, it naturally leads to the second half of the discussion. So let's start with
just really quick logistics here, Madan. We don't want to make sure that everybody can see what you're sharing, unfortunately, in the recording. Okay. So I'm not sure why it's not there. So it's showing, but maybe just leave it like this. Maybe. So just leave it like this. If I'm not sure whether it's presenting.
If you want to share in present mode, you have to tell Google to share your whole desktop.
Oh, okay. Okay, let me try that. Let's stop this.
Wow.
Yeah. That's okay. I'm going to leave this up and then go back to.
Feedback.
All right. All right. So back to basics. Oops. So let's start with some of the underlying principles behind ONOS clustering. So ONOS is set up as a cluster of distributed cluster of instances. So these instances are physically separate. They communicate with each other by passing messages. The communication happens over plain vanilla TCP connections. The different instances are set up in a symmetrical fashion. By this, what I mean is that the software that runs on each of these instances is exactly the same. This doesn't necessarily mean that they run exactly the same hardware specs. I mean, you are free to run like a different ONOS server for a particular instance. In fact, it would be ideal for a given service to take load in proportion to its capabilities, even though that is not something that we explicitly sort of do throughout, but that is something that naturally follows from where we are. And also a key reason why we make this distributed is we also want to be fault tolerant. ONOS should be able to survive node failures. How many node failures we can survive? Again, that depends on specifically how we manage state. It is, I can say that you need at least a majority of the cluster to be up and running for some of the key decisions to be made. Another key property is location transparency. By this, what we mean is that a client that interacts with ONOS can talk to any instance. To the external world, ONOS presents the illusion of a single logical instance. For example, if you're a client making REST calls, you can pick which instance you want to talk to at a per call basis. The system takes care of managing all the necessary state and everything on the client's behalf. And finally, the last one is not necessarily a feature; it's a limitation of where we are right now, which is today ONOS is the cluster is static in nature. By that, what we mean is that you configure ONOS to be of a particular size, and changing that size is not supported today. And that is what we want to address, and then that is what we'll talk about in this presentation. So let's look at what happens when a ONOS instance starts up. So this gives us some insight into what are the things that get looked at, what are the configuration that gets looked at, how nodes discover each other and so on, and we will take it from there. So when a node first comes up, one of the metadata information that it reads is a local file called cluster.json. This file has information about what other nodes are part of this cluster. From an implementation standpoint, you don't necessarily have to specify every single node that is part of the cluster. All you need is a set of key seed nodes that you can talk to. The idea is that these seed nodes serve as a point where everyone converge and then know about each other. But in the current implementation, if you're using some standard tools that that ship with the distribution, these files get auto-generated, and the auto-generated files actually list all the cluster nodes. Given that we don't necessarily support dynamic addition and removal of nodes, this is appropriate for where we are. So a node comes up, it reads this file, it knows about obviously its identity as well as the identity of other nodes in the cluster, and that is how it discovers nodes in the cluster. Now, once you discover the nodes, how do you know whether they are up or down? That is where the mechanism that ONOS uses to do membership and failure detection comes into picture. So what we do here is each node sends out periodic heartbeats to every other node in the cluster, and the specific failure detector that we use is called an accrual failure detector. Basically, what it does is, instead of painting the availability picture in black and white, saying that a node is either up or down, it gives you a probability of whether the node is up at any given point in time. And the idea is that this particular detector adapts itself to network conditions. So if a system is running under high load and therefore the heartbeats are like running a little slow, this takes that into consideration when it gives you a probability of whether the node is up or down. And this is how nodes are basically establishing these peer-to-peer connections, pinging each other, and that is how they build a picture of the entire cluster and the current state of the cluster. So if you go to the ONOS console and run nodes, this is the picture that you see. You see the different nodes in the cluster, and these nodes are discovered by loading the cluster.json file, and the state, which is the current state of the particular node as observed from this node, is captured by the failure detector reporting the appropriate status.
Are you tracking latency on the heartbeats too, or just does it succeed?
Right. So the way the failure detector works is that so the heartbeats are sent out at regular intervals, and we keep track of the inter-heartbeat arrival interval.
Okay.
And we keep track of the last n of those intervals, n being 100 or so, depending on how good you want the probability calculation to be. And then you set a threshold value saying that if the probability is above this, that is when I will mark the node as down.
Madan, is this always full match? So even if you have n is larger than 3.
Yes. In the current setup, a cluster of ONOS nodes, it is assumed that each node can talk to each other.
So you must have thought about that later on.
Yes,
Maybe
exactly.
Yeah.
Yeah. At some point in the future, we will get to federated control domains, and that is when this assumption is not valid.
So you said that you keep track of the last n responsive. Is that tracked per instance or is it the cluster wise?
It is pairwise. Pairwise. So each node keeps track of this interval with every other node that it is sort of pairwise.
So if one node happens to be located someplace else and its latency is low, that instance alone is indeed tracked differently.
Correct, because this computation happens on a pair of nodes, each pair, and the heartbeats are not back and forth in the sense that I send out a heartbeat, and that is how you know that I am still alive. And you send out a heartbeat. It's not that I send out a heartbeat and we respond to that.
That's sort of an interesting question. What if certain nodes can see each other but others can't?
Right.
Like do you decide it is so is a node up or down? Do the heartbeats have to be received by everyone, or can they just be received by a portion of them?
Right. So this picture that you built up is your picture. So even if you cannot reach, you will mark it as down, right?
Okay.
Just because someone else can reach it doesn't mean that you will mark it as up. So this is used.
global, and then based on presumably there's some sort of decision that's made for globally whether we're going to include a node or not.
Right.
That 3 of the nodes may say, "Oh, this guy's fine," but maybe everyone else can't see.
Right. And when we talk about the distributed primitives, some of this will become clear. I mean, it actually doesn't really make sense because the primitives for an operation to succeed requires a quorum or a majority, right? So whether the node is up or down, that is immaterial at that point. So let's actually sort of transition into the state management aspect, right? So we set up a cluster and everything, but clustering is usually something that you don't want to do unless you have to do it, because it introduces a lot of complexity, and one of this complexity is how do you manage state in a cluster of nodes and still guarantee certain properties, to the users of that particular, or basically people who manipulate that state. So let's look at some of the key principles that are underlying, the state management in ONOS. We consider it as a very, this is something at the core of ONOS. I mean, there's a lot of state that needs to be tracked in a network controller. There is network-related state. Applications bring their own state. All of this need to be tracked and tracked in a highly available fashion. And ONOS is responsible for taking care of that. And we believe this is a core value add that ONOS provides, to applications that run on top of it. And usually, this is doing state management in a distributed setting is usually the hardest problem, and we want to solve it once. Because we don't want an application that wants to run on top of ONOS to sort of deal with distributed consensus and payload detection and so on. These are things that should be available pre-packaged to applications that run on top of it. And again, as a result, applications just consume these primitives and they can just focus on writing the core network logic or business logic that they want to express. And to that end, ONOS exposes a set of primitives that cater to different use cases. Again, sometimes someone might say, I just need a put get interface. We believe that not every application just works with a put get API. I mean, there are different ways in which you want to interact with that state. There is a reason why Java util has so many classes in there. I mean, there are different ways in which you want to interact with the state, and that is something that we provide as part of these primitives. And most of you are familiar with CAP in the context of distributed systems and distributed state management. And usually the choices are are you consistent or are you available? The answer is somewhere in the middle, right? It's not always consistent or fully available. What you get is basically somewhere in the middle in that continuum. And you can talk about a shared nothing architecture where you are primarily using a in-memory data structure, which is local, like a Java map or something like that, where everything is local. Versus on the other end, you are talking about something like a replicated state machine, which manages state in a strongly consistent manner, provides linearizable consistency guarantees. And then you have somewhere in the middle where you are depending on how you access the data and where you read it from, you get different properties. And we realize that all of these are possible, and we try to provide primitives that cater to different use cases. So let's look at some of these primitives. Again, this will sort of make it clear how the cluster that we set up works together to manage some of this state. So let's look at the example of an eventually consistent map. This, as the name suggests, provides a map abstraction. So this provides a put get API. But the guarantees that it provides when it comes to consistency is that the consistency properties are eventually consistent. By that, what we mean is that when you do a put, that operation is replicated to all the nodes in the cluster in an asynchronous fashion. If this communication fails, we don't really make an attempt to deal with that and then fail the request or anything like that. So in some sense, this is the best effort replication mechanism. So we realized that some nodes can be down when this happened, and we have a protocol for fixing the divergence of the replicas in a background using a background mechanism called anti-entropy. The kind of properties that it provides is again depends on how your read and write access is. So for example, in this case, when a put happens on node A is responsible for generating a timestamp to assign a version to that update and then replicate that entry to all the nodes in the cluster. As long as your reads and writes are happening on A, this actually gives you pretty good consistency properties. But if you have readers and writers in different places, again, where you fall in the consistency continuum depends on the failures that are happening in the system and what keys you access from where and so on. Something that I would like to mention is that this is a data structure that we use to manage the topology state because there are certain properties of topology that for which an eventually consistent map is a good fit. For example, the reads and writes happen from the node which is the master for a given switch. So we always have these locality of reads and writes happening in a single location. And also by nature, these updates are happening on the data plane and you're trying to quickly reflect them in the control plane. So using a strongly consistent approach, you might be paying more cost and not necessarily getting the right properties based on the cost that you're paying. So this is one of the primitives that we offer. We use it for topology state management. Some applications use it for other managing their state. But as long as you're aware of the limitations and you're okay with that, this is a data structure that you can.
Before you go to the next level, so it also, I guess, implicitly, it implies that these changes can be observed in different order by different nodes. So
Exactly.
For instance, if you make a change on A, and then shortly as you make a change on B,
Right.
then C may see B changes earlier than A.
Exactly. And this is something that we discussed to a great detail when we talk about the topology changes, right? In fact, there is some sort of the mechanism that we use to generate the timestamp plays a key role in making sure these things get ordered appropriately at the destination. Just to give an example, if you're using this mechanism for doing topology state management, right? And an event that happened that was generated from A is that a port is up. And then later, an event that is generated from B is port is down, right? Depending on the order in which these get received at C, you might end up with an entirely different picture.
Yes.
But if you ensure that the timestamps that you use for each of these events is correct, we don't. That would be bad.
So what are you
Right.
doing then?
So we use a logical timestamp, which is based on like a mastership term for a given switch.
Okay.
So there has to be you have to pay some cost there to make sure that you generate in a sort of you do some coordination in generating that particular timestamp. Because using just pure wall clock time, clearly you are prone to clock drift and so on.
Yeah, but vector clocks are what you use, right? Basically.
Yeah, something like that. Not necessarily the vector clocks as it is described in the paper, but a variation of that. But that is what it is.
Same idea, whether it's for any, you don't have 8.1, 8.2,
Exactly.
or whatever.
Exactly.
Two other properties. One is that the anti-entropy mechanism ensures that eventually the state will be consistent across all nodes, which is not necessarily a property of an eventually consistent data structure.
That's sort of a good question, which is that the question with the eventual consistency some sort of interesting questions are one, does it actually ever reach a consistent state? That's an interesting question.
Good question.
Some systems resemble this that never reach a consistent state. That may be okay. That might not be.
Yep.
And the other question is, if it does reach this consistent state, how long does it usually take?
Yep.
Do you have any thoughts or comments on that?
Good question.
Or can you even observe that?
In theory, it is possible to never reach never converge.
If you're continuously churning.
If your churn rate is better,
Exactly.
is faster than the time it takes on the average for your tail.
And yeah,
But it is guaranteed that if you would, this is somewhat hypothetical, but I think it's important, but if you would stop.
Yes.
then
Yes,
the thing
exactly.
correct.
It will
Yeah.
converge.
So the property of, the textbook or Wikipedia definition of eventual consistency is once you stop writing to your
Yes,
system,
exactly. Good.
things will converge, right? But how long it takes to converge? In theory, it will never converge because this gossip mechanism can always pick the wrong set of nodes to talk to, and the guy who is actually out of sync, never really learns about it. So, but in practice, it's close to impossible for things to not converge if you don't have any writes coming in.
So here we use the partial ordinal sequence, right?
Sorry,
Partially ordered.
that is correct.
So that means only the last one update will guarantee the eventual working.
That is correct.
Yeah, you're not guaranteed to see the whole sequence of events.
Yeah,
Some
only the
events
last update.
may be
Yeah.
wrong if you receive
Yeah,
that.
if we got a new update, then we start from
Right,
the new.
right. Okay.
It's a partial update.
So because we have more,
Yeah,
go
this
ahead.
is
The
a- this
other
is
thing I was
background.
going to say is that it looks like here we do broadcast for all replication, and that's not necessarily well. So there's an inline, so to speak, replication that happens as part of the write, but then you get to choose when you build the primitive, like whether you want to broadcast to all nodes or whether you want to pick a specific node, like you have a function that a lambda you can define that picks a node, or whether you want to like pick random nodes or whatever. So you can say I want to inline with the write do. It's technically asynchronous because we don't wait for a reply, but we push out the messages in line,
And
and
then
then
you can tune the how.
you
long
can
you-
tune
Yeah.
how many replicas, so to speak, that you want to update in line. It's not always a broadcast.
So
Yeah.
just in the interest of time, this is I think just a background information that
Yeah.
so that when we deal with the complexity of adding and removing nodes,
Yeah.
we have a full understanding of what complexities will arise. So
Yeah.
you should probably try to let Madan
Yeah.
get through this.
Well,
No, it's
it sounds like,
it's
it
a question.
actually sounds like the opposite of what you're saying, which is that if people don't understand this, we're not going to be able to say anything intelligent about anything else. So we probably should make sure we're on the same page.
So I think the whole point of introducing this is to sort of bring out some of the limitations, right? So let's
Yeah.
get to the next part, right?
Yes.
So
No,
No. Not in this.
just
So the other, as I mentioned, we offer primitives that fall into different parts of the continuum, and then there are a bunch of primitives which give you strong consistency guarantees. These primitives are, like the state that we manage through these primitives is replicated for fault tolerance, and also it is partition. A property that is, or a limitation of, managing state in a strongly consistent manner is that there is a cost associated with strong consistency, which is the coordination overhead. And if you if you try to be symmetric, meaning everyone is part of the same thing, doing the same thing, and you're trying to scale, this doesn't work well because the coordination just grows linearly. For that reason, what we do is we partition the key space, and that gives us the property of scale for these primitives. So let's look at how this works in practice, right? Here I introduce another piece of metadata that is part of the ONOS cluster that currently resides or currently is deployed to the node. That tells you, or that tells the ONOS node how the cluster looks like, right? So this information is in a file called tablets.json that is deployed to the ONOS node, and the information that this file contains essentially, lets ONOS build that particular structure. So what you're seeing there is the different partitions that make up or that are formed in the ONOS cluster. There is a special partition called T0, which contains every single node in the cluster, which is backed by in-memory log. This particular partition, again, is not used for storing data long term, but it can be used for doing coordination style activities. For example, all the leadership election and things like that runs on this particular partition. The idea is that the data is not really long term. If you lose the data during a cluster restart, that's fine. But data that resides long term or that should stay for long term is basically split up amongst these set of n partitions. And right now, the default configuration builds up n partitions if you have an n node cluster. And as you can see, the partitions A, B, C, D, and E are the different nodes here. And then a given partition, you see which nodes form that partition. So as you can see, there is significant overlap. In fact, P1 has A, B, C, and P2 has B, C, D. So what this tells you is that there is if you take down a node, you are actually taking down a node not just from one partition but from multiple partitions. But the idea is that you pick these members of a partition to have independent failure modes. I mean, if all of them are in a single are attached to a single power supply, I mean that would not be very ideal. I mean, ideally, what you want to do is ensure that if a node fails, the failure that caused that particular node to go down doesn't also cause the other nodes to go down. But the benefit that we get out of this is that for a single partition, a node can go down, and then you can still take reads and writes on that partition. The other thing is partitions that or reads and writes that go to different partitions don't block on each other. A key property of a strongly consistent data structure is that it serializes all your reads and writes. So in this particular scheme, there is no reason for reads and writes that go to two different partitions to basically get serialized one behind the other. So let's look at how this works. I mean, I think I just explained how this works. So you take when you want to make an update, right? You map that key to a partition, okay? And we use a standard hash-based algorithm to do this. And then we know which set of nodes are responsible for that partition, and that is how we route the request to the right set of nodes. And in that partition, what we are doing is essentially doing a Raft consensus, running an instance of Raft consensus. So a node is elected as a leader amongst the set of 3 nodes, and that node is responsible for updating its log and making sure the log is replicated to a follower. And then there are lots of details in the Raft protocol that ensures that the integrity of the log is maintained in the face of failures, in the face of concurrent updates, and so on and so forth. So basically what we are doing here is running an instance of Raft for each of this partition. And that is how we maintain the integrity of the log in the face of failures, and also make sure these things remain resilient and so on.
So, a question.
Yeah.
You don't go first.
Oh, yeah, I mean, but by partition, you mean partition of the key space?
Partition of the key space, yes.
And you said 2 interesting things. One is that you said that typically strict consistency, imposes a global ordering on writes, and at the same time you said that the writes to different partitions
Correct.
don't have a ordering. So the ordering is only in the partition.
So let me qualify that by saying that within a partition, updates happening within a partition are serialized, but updates happening across partitions, we don't offer that guarantee. But I think I have the next slide which talks about how updates that span partitions work. You have a question.
You're partitioning using the hash standard.
Right.
So are you using the object hash code?
Sorry? No, I'm not using object hash code. This is something else, yeah.
Just one.
So I think, the properties of each of this partition is, you can have a minority of the partition down and still, take reads and writes on the partition. In a given partition, at a key level, the consistency that is offered is linearizable consistency. What this means is that it offers real-time guarantees with respect to the consistency of reads and writes. So once a write succeeds, every subsequent read, subsequent here being defined by the wall clock time, is guaranteed to see the update that was committed by the previous write, or any intervening write that happened before that. Another important property that we offer through this mechanism is that there is support for asynchronous ordered change notifications that are happening on a partition. You can register yourself for changes that are happening on a partition, and then you are guaranteed to receive them in the right order in which they happen. So this is an important property if you're trying to, say, for example, build a cache of changes that are happening in a partition locally. By subscribing to that update stream, you can essentially recreate the state of the state machine locally.
I try to place this in the sense of how much of this burden of partitioning and keeping separate is actually put on the code. So if I'm,
Yeah.
if I, let's say I'm writing an app and I need a
I have-
distributed key value store, first of all, is the key value store instance, which I'm going to use to store Boolean of key value pairs, is that already partitioned automatically?
I'll get to that.
You will next.
So just a quick note on how updates happen cross partitions. I mean, till now I mentioned about like how things map to a partition and like that particular update gets routed to the partition. If you have a kind of update where you're trying to update two keys, right? This usually happens, an example that we have is you're trying to make resource reservations and these reservations are stored in different partitions. Or the resources are stored in different partitions and you're trying to grab two of them, atomically, right? I mean, again, there is a way to do it. It's just that underlying that translates into a two-phase commit protocol that spans these two partitions. The key thing here is that none of this is visible to the user. And I will get to how we had that. These are the data structures that we offer for the users to work with. So all the complexities that I mentioned about partitions and leaders and everything, none of that is visible to the user. If you want to store some data, if you're an application and you want to maintain some state in ONOS, all you do is create an instance of consistent map, and everything is hidden from you. All the data is stored, in this partition scheme. You get the consistency guarantees, you get the durability, you get everything. Okay, and like the cross-partition updates that I mentioned, those all happen behind the scenes.
So we absorb the complexity, but at the same time left the developers with a choice to use the appropriate data structure and appropriate sort of a outward-facing abstraction for their data stores. So we're not trying to make any second guesses there as to what they want to do, but we give them simply an arsenal of tools to choose from.
Yeah.
So to achieve the serialization behavior across partitions, we need to specify some action or the default or the.
So yeah, I mean, when you create a consistent map, one of the inputs to building that is a serializer. It is what is used to serialize the key and the value that you have to a byte array. And in the partitions, all these store is these opaque byte arrays, right? I mean, and also keep in mind that these are all like generic in the sense that you can define your own key type, value type. This works like a Java map. In fact, consistent map has a method called as Java map, which gives you a map that you can work with. Whenever you have a map, you basically use an instance of this and create a map instance of that.
But you said that updates to keys across partitions are non-blocking.
Correct.
But in the previous slide, it looks like you said to
So you said there you actually want an update to happen atomically.
so the input comes from
Yeah, exactly. The user is saying that I want these two updates to happen, or I don't want. I mean, it is the atomicity property. So okay. So to the topic of the day. So there are a couple of things that I mentioned till now, which you must have noticed. It's like probably it sounds like a limitation, and it is, right? There are two pieces of metadata that we have in the system. One piece of metadata tells you which are all the nodes in the cluster. So basically, that is what we use for discovery. The second piece of metadata tells you, which partitions exist, which nodes are part of which partition, and so on. And today this metadata gets deployed to the node through some external mechanism. It is expected that data exists or those files exist on the node when the node starts. And there is no attempt made to synchronize these across different replicas. I mean, they get out of sync. The behavior is undefined. And also, if you for some reason want to change the metadata, A, you have to restart the entire cluster, and B, there is no guarantee that you will keep the data that you had till that point. And if we want to, support or be in a situation where I can start with a given size cluster, and then as my traffic grows or my network grows, I want to basically grow the cluster. This is not the right state for us to be in, and that is what we want to fix today.
Realistically, are you expecting clusters are really going to get that big? I mean, it seems to me that if you started up with an ONOS cluster that's got like 100 nodes in it, that 90 of them don't exist. They're just virtual, and that would probably be fine.
So I think growing is one use case. The other is there is a node that went down for whatever reason. It just crashed. I can no longer get the same IP or something like that. I mean, I'm trying to replace that with something else. So you can think of it as like a remove followed by an add.
Well, that doesn't seem like it. I mean, doesn't that work with existing ONOS? Can we do a live or running upgrade, hardware upgrade, like just bring the node down, then replace the hardware, whatever, turn it back on, and change it to same
You
IP?
have to give it the same identity.
You have to give it the same IP.
Doesn't sound like a terrible limitation.
So yeah, I mean, you could argue that, but I think there is something to say for elasticity because we got requests for adding some level of elasticity to be able to grow.
Yeah, it seems like it's nice, but maybe not terribly important to me at least.
Maybe, I mean, it might not be important for like say, I don't know, 50% or 80% of the users, but I think there is a set of like use cases for which you might want to start small and grow.
Also, if you use something like OpenFlow in your control network, it doesn't really matter what your nodes think may not matter. Okay.
So, I mean, one of the things that we want to do going forward is to extract this metadata out of these nodes and then put it in some logically centralized location that is accessible to all the nodes, and also that is where you go update your cluster metadata and use that to drive changes in your cluster. So that's the key idea here. Instead of this being static and deployed to every node out of band, let's move this out to a logically central location and then have the nodes access this metadata from that place. So what do we want the properties of this store to be, right? I mean, just like we know today where to find the metadata, which is on the local disk, we want this to be accessible at a well-known location, so that this is a piece of configuration that nodes will have that they will use to access the metadata store when they start up, right? So everything else basically they get it from the metadata store. We also want this to be strongly consistent. The reason for this is whenever you make changes to this metadata, it forces you to reorganize or rearrange state in your cluster, and usually that is an expensive operation. You don't want changes that you make today to be sort of, you don't want to make some changes that being visible to some guys and not being visible to others, and worse, you don't want updates to be lost or something like that. So we want this store to have a strongly consistent property. And finally, we don't want a situation where everyone who wants to access the latest metadata is continuously polling this store. We want support for asynchronous notifications, so that when a change happens, you can get notified, but otherwise, there is very lightweight or light load on the system, to keep track of these active sessions.
Is that because, I mean, polling presumably isn't bad if you don't poll more than frequently. Like if we poll once an hour, that's what even once a minute should be fine, right? How are you expecting that this will change rapidly, or is it that you just want it to react very quickly when it does?
How rapidly it changes, I don't expect it to change rapidly. But when it does change, we want someone to be who is dependent on the metadata to update themselves fairly quickly. Because having stale metadata, remember, this is not just used by the cluster nodes that are starting up. This can also be used by the clients of ONOS who wants to know, where should I go talk to, to basically get particular service done.
The basis for load balancers and stuff like that.
It seems that this will largely happen on kind of a human timescale, so maybe updating it that quickly.
It could be. I mean, again, depending on your deployment, and also sometimes these kind of SLAs are set by the administrator or the operator of the system. So, what are the choices for this particular metadata store, right? There are certain things which emerged as standards in the industry. Zookeeper has been like a well-known solution for maintaining metadata. XCD these days is another solution for keeping track of cluster metadata. And if your deployment already has one of these things deployed, if you're running this part of a data center cluster and you already have a config store that where you are keeping track of this kind of information, absolutely it makes sense. Because I know that if you're running a Mesos cluster, Mesos already has a zookeeper to elect the leader who will be doing all the resource allocations and so on. If you already have something like that, there is no reason why you should not be able to use that. Because all you're doing is keeping some piece of metadata there that you want to access, and you want that to be strongly consistent and available. So it makes sense for you to use that if you already have it.
Not only that, but also with these two choices, you don't have to worry about polling because both of them provides asynchronous callbacks
Right.
to everyone that there's a change. So
And so does the primitives that we have in ONOS. So, and if you don't want to take on another dependency in addition to ONOS, then another option is, just run a bare bones, ONOS cluster, which is essentially all it is running is the store. Okay, and obviously, basically that's part of the core. So what you have is, this cluster has statically configured metadata. It has a single partition. You replicate it like for availability, but this is at a well-known location. Your regular ONOS cluster basically talks to it to store metadata, to access metadata. We already have support for asynchronous notification. So again, this is something, if you don't want to take on another dependency on a different store, this is a valid option for you to go, and this satisfies the properties that we want of the store.
I
Right.
guess there's this sort of chicken and egg problem. The question is, how many levels do you want to solve it? And your hypothesis is one should be fine, or something like that.
Yeah. Because at some point you need to fix something, right? Because this is dynamic, but you are now building another cluster. If this becomes a recursive problem where now how do I discover that cluster and so on and so forth, this is never ending. So at some point you need to fix the configuration. And usually that is what a Zookeeper cluster or something like that. In Zookeeper, you have to specify exactly where your nodes are, who your peers are, right? This is not something that you discover on the fly.
Why couldn't you discover it on the fly? I guess.
So now you're moving problem to that another service, which will support the discovery.
but not all problems.
I mean, you can imagine doing this via like MDNS, right? Where I just do an MDNS lookup to find out where my metadata server, or say DNS or MDNS lookup to find who's my metadata server, what's their IP address or MAC address, and it just tells me, right? That would be, that'd be one way to. It should be very simple, right?
As long as it satisfies the properties that we want this particular store to satisfy, then why not even make that your first line of metadata store, right? So I mean, the key thing is this is, as long as the solution that you have satisfies those properties, it's fine to use it. The other thing, again, this is all these choices gives you different levels of flexibility, but they also impose different constraints, right? The other solution is you have your regular ONOS cluster, but what you're going to do is you're going to ping the metadata store to a given partition. So that particular partition is statically configured, right? And now you can grow or shrink around that, but you cannot take those things out, right? Or at least you cannot take a majority of that particular partition out.
Why can't it be the P0 partition? It doesn't have that specificity.
So P0 is something that keeps growing, right? Because P0 is something that is in response to when you add a node, right? So for example, if you start with it is in memory. It doesn't store any data. So if you restart it, you basically lose that particular state. And B, that is something that if you want to fix that, P0 is not a good candidate for that. And secondly, this is something that you don't want to pay a lot of cost of like synchronization or coordination in that particular partition. Usually 3 nodes is fine for like fault tolerance reasons. But if you have like a 100 node ONOS cluster, you don't want every single metadata read and write to actually be coordinated across 100 nodes.
So with the risk of risking that you guys are going to chase me out the door with a big stick.
No, but this is perfectly fine to ask. This is why we're here. I just want to make sure we didn't auger in too much on the preliminary materials. That's all my point.
So anyway, so what is your opinion about the way Acha solve this?
Does Acha
How would Acha handles cluster membership and cluster joining and cluster dynamically shrinking? Do you have a specific criticism how they solve this?
So Acha uses similar concepts. I know that their failure detector is also based on the accrual failure detector that I mentioned.
Yes. Yes.
But that is not the biggest or the most complex piece of feature that you implement. I mean, Acha is a framework for writing these applications. It's not necessarily, I mean, you need to build something on top of it.
No, what I'm saying is that specifically the way Acha handles the cluster joining and how it supports that you can dynamically add the remove nodes from a cluster.
Right.
It doesn't rely on another instance of some other cluster.
Right.
You have one bootstrap information you need to have, which is at least the first few nodes.
Right.
But you have one node that has to be able to bootstrap itself and join itself.
Yeah.
And then
Usually you have a set of seed nodes.
Yes,
and then they all
in a
get
system where there is an entity, whether that's Kubernetes or some sort of platform manager, that happens to know the IP addresses and can provide that seed information so that these nodes can find each other. And once they find each other, then the cluster can be formed dynamically. Both grow and shrink.
Yeah. So the idea is that one point there is that it's a fully decentralized architecture in the sense that each node decides exactly what role it should take on, right? So there are two parts to it. One is how do you detect other members in the cluster, right? The second part to it is how do you ensure each node is responsible for the right portion of the key space. Okay, so this is classic Dynamo architecture, right? So it's a fully decentralized system. So when you add a new node, it detects other nodes in the cluster. It also has these like virtual positions on the consistent hashing tree that tells you which portions of the key space that it should take ownership for, and that it basically initiates a background process for doing this migration of data from their previous nodes and so on. So I worked on Dynamo, and I know that there is a lot of value in putting the metadata out. Trying to have the same cluster manage data as well as metadata. Usually, from experience, it has led to systems that are hard to converge, and also like the failure modes are difficult. So, and also I haven't worked with Acha per se, so I cannot exactly comment on exactly how they do it. So finally, now this is the point where we talk about so now you have pulled out metadata. How do you now grow and shrink the cluster, right? So the idea is that we will have a fixed number of partitions in the cluster, right? So today, if you start with an n-node cluster, you have n partitions. But going forward, the idea is that you pick a fixed number of partitions. It can be 8, it can be 16. Depends on what your growth projections are, right? And as you grow and shrink the cluster, what we are going to do is redistribute these partitions in order to ensure load distribution. Okay, so the idea is that roughly we want each node to be a participant in the same number of partitions. Okay, so we know that a partition will have 3 members. So what we want to do is we want roughly each node to be responsible for the same number of partitions. If you add a node, some node will hand over its partition to the new node, so that now has one less partition, and this new node has one more partition.
That will use consistent hashing so that the churn is minimized.
So you can do consistent hashing. I mean, usually that is how you minimize it. Or you can use any other mechanism that minimizes the churn, right? Usually consistent hashing is a good idea. There is the other way to look at it is, say for example, I add a node and that node happens to be like my high-end server that I just bought, right? I know that it can actually take twice the load as an existing node in the cluster. So I can actually configure it to take like twice the number of partitions. If that is how I want to have a load balance. Again, load balancing here is not just same number of partitions, but the number of partitions in proportion to its capacity, right? But the idea is that whether we use consistent hashing or whether we use a different approach, the idea is to pick the mapping, the new mapping that will be in place when the new node joins the cluster.
That sounds like a really good idea. So how's the system aware of the relative sort of performance and capacity of different nodes so that nodes how to properly balance the partitions?
So some of this is static. Like say if you know that a given instance that you're adding is twice as powerful as an existing instance. I mean, just purely based on hardware specifications, right? That could be one indication. The other thing is sometimes you can end up with nodes that are taking more work than other nodes, just so because they happen to be managing a hot partition.
Yeah, that could be an issue.
Right.
Right.
Usually that is an issue, right? Because if you have This happens, when you have, if your partitions, if users map to partitions and you have a very active user, then usually it becomes like really hot there. Sometimes you split that, but then now you have a partition which has the active user. So there's no perfect solution there than to, make sure you don't do expensive operations for every single user interaction. But again, that might not always be possible. But again, there's no perfect solution there.
But you are inclining to use a static solution here first, right?
Yes.
Pragmatic.
I mean, that is the idea. So,
Okay, so you're not trying to solve the problem with dynamic load balancing.
No.
Even over a long period of time, which
No.
is probably where these things will become obvious. Or,
So
It's just I think stone.
is the idea you have a fixed number of positions and then you use P0 to negotiate the addition and removal of members from each partition?
Okay. So do I have a slide for that? No. The metadata store will be updated with the new partition placement. Okay, and that drives everything. So
everybody reads that.
correct.
There may be a small period of time where all
Yes.
the nodes are.
Because remember that this is not a flip, because this is a process that we need to initiate, and this is the slide that sort of explains that, right? So if you're trying to move a partition from C to D, right, this is not a simple operation because you could be moving a lot of data. So what you do is, B joins that partition, right? Now you have 4 members in the partition, and when a new node joins the partition, the RAF protocol ensures that the new node basically catches up and has the same log that everyone else has in the system. And once it gets to a state where it is now up to date with what the leader has, that is when it can update the metadata store saying that now I am ready, right? And then that basically triggers, so C will be listening to that. And C will see that, oh, the guy who just joined is now active, so I can now leave the partition. So this is done to ensure that you don't have a window where you have less sort of replication or a replication factor for a given piece of data.
You can tolerate a failure within that window of time.
Yes. So going back to relying on some metadata store, the zookeeper entity you wanted on the ONOS cluster.
Yep.
Is there any other solution, or are these the ones that you perhaps consider and solicit feedback on?
It's also the same cluster with
Same cluster.
fixed. It's also the same ONOS cluster where we fix the partition. One partition only to hold the consistent data.
That's good.
And clearly, within that partition, the same constraints that apply today would apply tomorrow. Meaning that if you want to replace a node within the partition, you can do that, but you need to bring them up with the same identity.
Could you migrate the pinning?
Yeah.
Could you say I want to move, like this node is, this cluster, this partition's got 2 nodes now, and all the distance coming back, and I migrate?
So so remember that every node, when it comes up, a static piece of information that it has is where to find the metadata store, right? It will, that, ABC is what you have already pre-configured, that's part of their configuration with which they deploy them. If you update the membership of that particular partition, then you need a way to update like the new nodes that are coming up.
Well, presumably you're either coming up as someone who's going to be a bootstrap node, like a super node, or you're coming up with like as a slave, where you either have an IP address, you can go get bootstrap,
Right.
or you can, it's a remote metadata service like Zookeeper or whatever, right? So as long as you have a pointer to something and you know what the protocol you need to speak to that something is, any node can come up as a slave, and as long as one of the nodes can point you in the right direction, it seems like the bootstrap process for slaves is not so bad.
Right. So you need one of ABC to be available, right? You can actually replace C with E, but the clients will try to talk to C.
Hard to see, yeah.
They will fail. They will fall back to A. They can talk to A. So they will, but you cannot replace. So I think when I say that a majority of replica set must stay on, maybe that should be, at least one should be stay on and it should be available.
One of A, B, or C
Yeah.
should be available in given time.
Exactly.
Or the
I
thing
think
is,
that's a very mild
if you
requirement.
That's kind of
if you connect to a server, right? Any server that's part of the bigger cluster, it should be able to respond with like a forward, right? Which is like, I'm not a bootstrap node, but contact one of these other nodes because it knows what it has access to the full metadata.
Right.
Service.
Yeah, and also other thing is you can once you contact A, and A tells you that, by the way, the metadata servers have changed. They are now like A, D, and E. You can actually use that to update your local self, so that next time you come up, you can talk to A, D, and E, and instead of B and C. So yeah, I think you can sort of, there is some leeway there with respect to how you manage that particular partition.
But the external clients then they have to configure with the core discovery cluster or partition. We would have a way of notifying them also.
Yeah.
Internally, we have that notification.
Yeah.
Yeah, I mean, if your APIs are RESTful APIs, it could even be exposed as a redirect and HTTP code sends them.
Yeah. So I have a
On top of having the three IP addresses available to all parties, and they can do the fallback.
Right.
So that could be multiple options.
And I mean, I think as we were talking about client interaction, right? So the way clients discover where your cluster is, they talk to the config store. Config store responds with like the current membership of the cluster, which can be cached, and you can use that to talk to the cluster. You can sort of lazily detect like basically stale cache entries and then evict them. Like say for example, you used to talk to entry A. You have an entry for node A and you talk to node A and node A is not available. That might force you to go to metadata store again to basically fetch the latest information. So there is some.
Could you use DNS for cluster configuration, right? If you only need one node,
Great.
DNS, right? You can put shallow DTLs on there. All you have to do is update a DNS server with the IP address of the nodes that can provide for sure.
I mean, again, this is, you can use anything as long as it.
Yeah. So I guess the difference though is if you have if cluster configuration is actually going to contain the metadata, then it needs to be strongly consistent. If cluster configuration is a pointer to one of the nodes that can provide you with bootstrap information, then it can be eventually consistent. It can be anything.
That is true. Yeah.
Hard coded to any IP in the cluster as long as what it was or something.
So right now we I mean, because the approach calls for storing some additional metadata and not just a pointer, like the placement of partitions and like ownership and so on.
But if you put that into one of the partitions, like a fixed partition within the running cluster,
That's right.
then all
That's
you need is a
Exactly.
Are you looking for one of these four options, or are you considering
So,
providing alternatives?
So what we might, again, the thing is, all of these are possible. And the way the code is written is that all you need to do is plug in appropriate metadata store implementation.
Okay.
Right. So we already have a store which is backed by a file. Right. All we need to do is write a store which gets that information from a store. Right. We think that the options that either using it like basically pinning the partition to a in an existing cluster is something that you will get out of the box.
Okay,
Right.
that's good. That's good. I would say that's great because in terms of kind of purists of ourselves, hope that's a nice purist solution.
Right.
On the other hand, I would say that in practice, having an assumption that either zookeeper or etcd is available is not a total request. It's I would say any system that you would consider that's almost given.
Yeah.
If it's either, if you assume that it's zookeeper, you will go with only one of them and we won't support those. Then it becomes tricky because now etcd is not showing as zookeeper steady, so that could create a problem. But if you can support both, I don't think that is.
It's going to be a client that you write. I mean, etcd is essentially backed by a distributed key value store.
Yes.
I mean, it has a HTTP interface.
Yes.
All you're doing is calling this key value store, grabbing some information, and it has the ability to you can do long polling and things like that.
Okay. But in terms of ONOS as a project and in terms of the existing developers, are you saying that you will be committed to get the PIN solution in the code base, but it's architected in such a way that if somebody wants to instance for whatever reason,
Yes.
Use etcd or
Right.
zookeeper, they're welcome to develop the corresponding.
Exactly. And we expect that to be a minor project. It's not like
Basically just drop in a class and then maybe
No, I
just
understand.
configure it and then that's it.
It's a compile time change, not a runtime change.
Well, I mean, we can make a runtime change because it's really just need to have a class loaded and then be able to map to it.
Like find follow the protocol, which Java does for the protocols.
I don't
And have
think
it
it
look
has
for
to be a runtime change.
Well, I don't want to necessarily have to recompile all of ONOS and redo the build process.
Well, so it could definitely be a configuration change.
Yeah.
Where you basically provide like either like the client class.
Exactly.
It's either
Exactly.
the local one, file-based one, or
Exactly.
zookeeper backed
And
store.
so it'll be fronted with some sort of a factory.
That's not.
I mean, the other sort of consideration is, what is the right number of partitions, right? I mean, we're talking about like a fixed number of partitions. As I said, pick a reasonable number. The reasonable here being, if you have a 3-node cluster, something like 6 or 8 is fine. Keep in mind that there are certain things that you pay when you have more partitions. So one is the updates that you make cross partitions. Even though you don't really have to code anything for it, they're expensive. In the back end, the way we do those updates are they require a 2-phase commit protocol. So there are more steps in getting those updates done. The other thing is there is a small amount of network traffic that is there for each partition, which is the leader sort of sends out these heartbeats to the followers to make sure they are there, and also whenever a change happens, that gets replicated. But again, replicating real changes is something that happens in a small cluster, or a small partition or a large partition. But the cross partition use case or update use case is something to keep in mind. And also keep in mind that someone will, creating like a 100-node ONOS cluster. Much before that, you'll probably federate your control domain to have smaller domains which closely coordinate with each other. So while yes, it is in theory someone can do it, but I would never create like a 100 partition cluster, because the chances that you have a 100-node ONOS cluster is very small. Much before that, you will end up federating your control domains into smaller pieces.
So if I start out and putting this in some of the practical use cases that we're looking for ONOS to solve, I started the smallest cluster tree, and let's say we would go up, gut feel up to 10. What would be the usages, including 16 or something?
16 is a reasonable
that is not going to create that overhead that.
No, I think for example, we do, as I said, the overhead is the sort of the heartbeat overhead is fairly low. I think the default heartbeat interval right now is 3 seconds, right? And you are basically sending out a small, a heartbeat every 3 seconds.
This cross partition coordination that only happens in certain type of.
Yeah, and also it depends on the specific. Most of the applications that we have seen so far, they operate it on a single key, right? There are some applications one use case is the resource manager, where you do a coordinated update across multiple keys. That is where you pay the cost of cross partitions. And in fact, you can do some clever magic on how you pick your keys, so that you land keys that get modified together in a single partition, so that updates like that tend to go to single partition. And internally, we take care of if all your updates, even though they are a composite update, if they happen to land on a single partition, there is no 2-phase commit. So it's basically a single operation that you submit. And the other thing is, at some point in the future, we might look into providing ability to split a partition or merge a partition. But I'm going to tell you that it's very complex operation with a lot of edge cases, and we would rather focus our energies on solving or making other parts of the system more robust than focusing on that.
It's specifically the transaction. There needs to be a transaction context to get the atomic multi-key operation, and that's a very, very small percentage of the current use case.
Yeah. So that's all the prepared material that I had. So we can talk for it.
So what did you hope to get out from this?
Obviously, if you guys have comments, or what you any feedback on the approach, anything that you
On the base assumptions too, right?
Yep.
So the idea here is to validate the base assumptions and to get any feedback on the current plan, whether it's clearly if the assumptions are wrong, then, or let's say that you expect a dynamic churn in your cluster. Then you can have a discussion about that. We voiced our opinion and stand on this, and that's kind of what we're hoping to get out.
So the churn, I agree. It's not going to be. We're not going to be churning 20 changes a second. That's not that churn here, right? We're talking about in a controlled environment such as under Mesos or Kubernetes, where a failure happens and I bring up another one that will come up under a different IP address and it needs to join the cluster. That new pod comes up, that type of thing. Again, if it's happening 20 a second, we got bigger problems in the system. The question is, how do we, when a pod comes up in Kubernetes, a new system comes up, how do we inform the cluster that, hey, here's a new member of the cluster, right? And what type of churn happens on each instance of ONOS when that happens? So today, when I form a cluster on an existing thing, even on the initial bootstrap, everything does an update 0 of graph, and essentially I do a reboot of the system. That I'd like to avoid.
Which is precisely why we're doing it.
Really, I mean, you can unplug one on a server and plug in another one, and THCP assigns the same IP address, and you're good to go, right? I mean, in some sense.
But you're
Like
correct.
replacing an existing server. I mean, the failure mode of like replacing an existing server seems that's not so hard to handle in the existing.
So what this allows us to do is not to get in a position where the deployers would over provision just in preparation for some future load. So they can start small on a small piece of network, then they can put additional areas of network in the same control domain, but in order to be able to cope with the load, they need to be able to grow the cluster size. And so it's really mostly in support of those use cases that we build this capability. And we try to ground it with some pragmatic assumptions and limitations, which cut out, it's 80-20, right? We cut out those 20% which cause us the 80% of the problems and the edge cases and complexity throughout the system. So that's kind of what we're aiming for here.
So if that's the use case, do you have any thoughts on sort of how your ONOS cluster performance improves over, if you add more nodes? I mean, like we think it improves pretty linearly up to 8. But how about, as you go up to 100, like what's the saturation point where like adding more nodes doesn't actually improve your performance?
So we have data till 7, right? We have
Till 70?
Sorry, 7, right? 3 to 5.
70 would be really good, right?
So when we can extrapolate, I mean that's what we can do from the data that we have. I mean, we have seen that certain operations obviously gain when you add more capacity, and usually these operations tend to be not something that involves everyone to coordinate, right? I mean, clearly the only way you can scale is to basically limit the amount of coordination to a small group, and you have more groups that can independently work on it. And that is what we observed for those operations. I mean, these operations included like the amount of we can increase the number of switches and also increase the number of flow rules that you can update on those switches and so on. But we don't have any data for like how things will look like when you go to 70. But based on the architecture, we feel that this should scale pretty linearly, especially the aspects that touch the store, and usually those tend to be the ones that are like slowing down your system. Given that the goal is to minimize the coordination, there is nothing that touches every single instance for an operation. So that would cause us to make sure we limit the work to isolated islands, and that is what we think will cause this to scale well.
Just another question is, what sort of have you seen applications and network loads that really basically don't work well on an 8-node cluster and you need something that's bigger? Or do you have any thought about how obviously it depends on workload.
Yeah.
But what kinds of workloads?
That's very different.
What kinds of workloads would
It's hard
kill
to.
it? I mean, have you seen? I guess the question is, have you seen any existing workloads that basically push ONOS to its limits? Where
Only the synthetic ones, really, right?
Yeah.
When we were doing on purpose loading and specific. So it's gonna be it's a basically multi-dimensional problem that it's a function that will involve things like clearly the I/O induced by the number of devices and frequency of the control interactions we have in them, right? It's the potentially port density may affect it, but the size of the flow space that may affect it, and the dynamic nature of the flow space, which will translate into the frequency of the control interactions. So I think it's a multifaceted problem. So I don't think we can really guess. It would be best to observe it. We can have some rough goals about how many devices or how many ports to put under the scope of a single controller. that will be limited by our I/O memory as well as compute capacity. We can make predictions. Is there going to be 200 devices? Is it going to be 500 devices or 1,000 devices? I don't know. That's going to be it's difficult, but it's going to be some number, right?
On the workload and the application.
Exactly.
So,
More specifically, depends on whether that workload is, what percentage of that workload requires the coordination? Because if you have a workload that doesn't require any coordination, very little coordination, then it should scale fairly linear.
Right.
You will only see nonlinear scaling where workload involves lots of coordination. And even that sounds like it is not that variable. So
it does seem that things like kind of global routing as your network gets really huge require more and more coordination because you're traversing more and more, network segments that are controlled by different ONOS instances.
Right.
So that's maybe just maybe global routing itself is one of those things.
And also depending on the nature of your flows, right? Usually, at least an expectation is that if you have multiple control domains, each managing a piece of network, if you have a lot of flows that are just local to that domain, you don't even have to coordinate with some remote entity, right? You only coordinate when the flow, the something that you're setting up actually touches or traverses their domain.
Well, if you think if your network, is getting bigger and bigger, and you're having more things, more flows that traverse the whole entire network, and need, say, to reserve, they're doing resource reservations that require some coordination.
But if you look at entities that could reasonably, that a provider or operator might want to reasonably consider a control domain, whether it's a data center or a region, fault region and data center, or whether it's a specific transit network or a central office, those things I can imagine being a control domain. That would be run by a cluster of ONOS instances. Some of those may be mildly distributed in nature. But then beyond that, we might be straying into the realm of federating. And so we want to be careful is not to intrude into that space too much. We want to have be able to have an ONOS cluster that can accommodate a reasonably sized control domain.
Yeah, but I think those three examples you pointed out are good ones. The ones the central office, the data center, and the metro network, right? Are all kind of.
Have you given any thought? So, say you have a 3-node cluster managing 300 devices, using 100 each, right? I want to add a fourth node. Now, these are open flow devices. How do I move this device into that?
Excellent question. So
And the other alternative, I have 5 and going down to 4.
Right, because you also need to be able to reach out and touch the devices and tell them, guess what? There's a new boss in town, right? So for that, we actually, even in Cardinal, we've modeled one of the device behaviors, which we have not implemented yet. It's called open flow configuration behavior or something like that, or open flow configurator, that provides an abstraction for an application or some sort of an entity to be able to tell and remove controllers from a device.
Okay.
Now, there's nothing to do with, I think this one is specifically for open flow, but we can model it, we can maybe step back and make it maybe open flow independent too, potentially. And the idea here is to use whatever protocols are appropriate, whether it's ODSDB, whether it's netconf, whether it's SNMP, CLI, doesn't matter, to be able to reach out and touch the device to introduce the new member of the cluster to the device.
So as your cluster changes size, either up or down,
Potentially even say, you know what, you should, because some devices may have limitations that may not allow it to know about every 13 instance, right?
Yeah.
All 13, you may have room for 3.
Right.
And so now it's up to some sort of a load balancing application to be able to determine which of the 3 nodes you should be taught to that device.
So which protocols do you implement it for? Do you implement it for?
We have not implemented it. We modeled it in anticipation. If you look at one of the ONOS architecture diagrams, that has the many little boxes. One of them is called adoption. And that's basically sort of ability to reach out and touch a device and tell it, you're one of mine.
Do you see this in Emu or Goose or Falcon?
So it's not part of this effort. I think what Madan or is working on is really just to deal with the mechanics of increasing the cluster size in a controlled manner without losing data. And then the rest of the surrounding functionality, which may involve in load balancing partitions based on some heuristics or external data, or load balancing devices which report, those are extremely activities which will be enabled and will soon be demanded because of that capability.
So currently then, the switches basically have to be configured out of band, is that correct?
Essentially, yes, but it will through common abstraction.
Yeah, so well, maybe not, well, it's out of band, right, outside of the purview of ONOS, right, so if
No, it would be through ONOS.
well, currently, okay.
So
You
currently,
could do it outside of
currently you can do it through ONOS, nobody's stopping you, but we want to be able to have ONOS have a essentially load balancing application which can take a load, independent of even changing the cluster size.
Yeah,
You should be
I
able to
mean,
look at
so
the
like-
devices and rebalance.
Are you saying then that ONOS can or cannot, tell a switch which controllers it should connect to? Because there is this bootstrapping thing. When a switch boots up, it doesn't know what it doesn't know. Cannot. So maybe I'm trying to clarify what I'm saying. That currently it appears that to bootstrap your switches and configure them, you need to do that outside of ONOS.
That's correct.
Using some out-of-band mechanism, like if they're OBS switches, I have to configure them using OBS DB. If they're netconf switches, I have to connect them use netconf. If they're HP, I can use CLI or SNMP.
Exactly.
Yeah.
I mean, netconf can be configured through ONOS, right? I mean, this is something that you connect to the device.
Yeah.
So-
So, but what we want to do.
So what you're saying is, if I understand you correctly, is that I could write an app that calls ONOS's netconf subsystem, or maybe it's OBSDB subsystem if something exists, and manually use that to configure my switches.
Yeah, but we want to avoid doing that using specific protocols.
Yeah.
And instead, house that capability in the device driver subsystem and front that capability with a common abstraction, which basically says add, remove control, add device for a given device, add or remove controller or list controller, and that's it.
That's modeled today, but it's not implemented. So there's no API today I can call that says,
What do you
hey,
mean
adopt
modeled?
it.
That modeled is in terms of we have a Java
interface.
Oh, there's okay.
But we were, so it was sketched
but no
out in Cardinal, but not implemented because we foreseen that this was going to be needed. So the interface may need to be adjusted as a result of learnings, but the idea is to implement such behavior.
But even in terms of bootstrap, you could almost point the device, say, look, I'm going to ship my device as pre-programmed with some name. I'll contact the controller via load balancer, so I always get one, and then it'll get redirected, adopted by a specific one.
Precisely.
Yeah, I mean, there's.
Yeah, so that's how you can actually get,
And then you can
close to
bootstrap
zero
that way.
config stuff.
Yeah.
Yeah, I mean, there are lots of things. You can imagine also that whatever, I forget what it's called, but the various, switch bootstrapping mechanisms. When they ask, who's my boot server? Well, you could tell them in configuration that's specified by ONOS, or maybe it could even be routed to ONOS, and ONOS would say, oh, your switch line, here you go, or whatever.
Yep.
So today, when you have, let's say, you have a 3-node cluster, and let's say I pre-program every of my switches to point to those 3. But you do a load balancing in terms of who is the primary for every given, right? Do you do it by simply reject the other nodes, simply rejecting or not responding to the
So there is this feature is available. You can directly do it from the UI or do it from the console. You run balance masters. So what it does is we actually do a handover protocol. So when a switch connects, it basically connects to all the controllers that it is configured to, right? So everyone starts out in a standby state and they run for election. One of them gets elected and then they set their role to be master.
So if we're talking about an OpenFlow device that has like 1.0 with nice area extensions, we use the nice area mastership extensions 1.1.
Okay.
It's part of the OpenFlow spec, where the controller that wins the ONOS leadership race asserts itself as master on the device.
But I guess the other interesting question is under what conditions and what mechanism does ONOS use to rebalance switches when when nodes go up and down or when switches go up and down?
Yeah. So the mechanism to rebalance. Let's take the
The
non-failure.
mechanism is you reassign the mastership. But I guess what sort of is the default algorithm or policy?
The thing is the leader election, right? I mean, if you don't do anything, it's sort of random. Right? So anyone who is vying for leadership can become a leader, right? But if you want to balance, then you are trying to move leadership from A to B, right? So the way, the leadership service, what it does is whenever you elect or try to become a leader, you basically get into a queue. Okay, and this is an ordered queue. And right now, the idea is that whoever gets in there first basically becomes the next leader. But the expectation is that this particular queue is a priority queue based on some parameter that you configure. You can say that I want the priority to be based on proximity to the switch. Okay, that basically puts that particular controller at the top of the queue. So if you want to become the leader, then that guy basically gets the preference. So we have this mechanism to make sure we can hand off leadership from A to B. So what we do when we want to do this handover is we instruct the current master. We basically do two things. We first move the guy where we want to leadership to the top of the queue, and then we instruct the current master to step down. Right, so the order automatically elects the guy to become the master. And then there is more when we make sure the flow rules are appropriately backed up and all that. But that is the idea.
So two questions. The dynamic stuff. One is it's targeted for Falcon. What's its current state?
It's aimed for it. So what Madan presented is aiming for email.
Oh, really?
Okay. And what about the adoption? Is that even
So that
has it been
is not-
even
that is
envisioned
not
yet?
So well. So that's been envisioned, but it's not planned for email. I don't expect the complexity of that should be much lower.
If someone picked it up from the community, it could be put in uni, but
Right now, right now,
Just stick that in there, didn't you?
right now, yeah, cord use cases dictating the priorities of the tasks. And there are some tasks, such as this one, that we try to still maintain just because you have to maintain some level of balance, right? Where we try to move the platform capabilities forward. You can't be entirely subjected to just the short-term priorities. That would not be helpful.
Okay.
Not for a long period of time.
It's a 3-month release cycle. So November.
December.
Okay. I thought it was targeted for November.
Well, end of November
So
is like
it's
the target date.
November 32nd? Okay.
Probably more like
The-
36.
The cadence has been that, we usually
Yeah.
target at the end of the month, and then by the time we sort of get QA finalization
Right.
and artifacts built and stuff, it's the first week.
First weekend. Fair enough.
All right. So
You should adopt the climate interaction.
Mhm.
So suppose we have a relation,
Sorry?
the balancer operation.
Uh-huh.
So for that, the load balancer track the request from client, like you can request whatever. So how the load balancer will connect to the ONOS instance, like A, B, just use IP address?
Oh, the ONOS, sorry.
Yeah, just after the load balancer get the request, how the load balancer send this request to the different.
Oh, okay. So usually the load balancer, most of the load balancers are configured with a strategy for picking where to send the next request. It is usually, sometimes it is based on the number of open connections to a given instance, or what it does is it tries to avoid sending to a node that it knows is down. So most of the load balancers, they keep track of the health of the services or the servers behind them. And if a node is down or not responding to heartbeats, it basically doesn't send any more traffic to it. The interaction with the configuration is so that it knows the set of nodes that are part of this cluster, right? So it doesn't really tell you whether they are up or down. That is determined based on the load balancer heartbeating, or basically then servers responding to load balancer heartbeats.
So the load balancer know the different instances running or down.
Yes.
Kind of
Yes.
So,
Yeah.
So what I'm is if we just send out the request like to instance A, before we send it, load balancer know instance A is running. But after load balancer request to A, A got this required.
And
At this moment,
Sure.
crash.
it's a failed request. So you have to, the client basically gets an error. So if it's a REST call, then it will be
Load
like
balancer
500.
can detect this event and then
Yes.
send it. But load balancer still keep the request. Right? Keep
No,
on-
No, fail it probably.
So that means the request got lost.
Well, it wasn't replied to.
So the client would
will
just,
know that it
there'd be a
can-
reach-
would client
there'd be a
will know that
retry. The client would have a
Client-
retry.
the client can retry.
Client retry.
Yeah, retry. And our use case is a little different here because we're not going to get the load balancer information from your cluster information. Right? There's potentially this other system that's managing the health and the birth and death of cluster members, and it's going to inform the load balancer.
It's also a potential candidate for your metadata.
Yes.
Cluster metadata.
Yes.
I think in tree cluster there in the definition there are the IP prefix. So right now,
Yes.
all the for one cluster, all the IP should belonging to one IP.
Yeah.
We give it the IP prefix. Why we did that?
The IP prefix is just to pick the right NIC on the ONOS instance to use. So the IP prefix can be different for every.
No, I'm sorry.
Yeah. So.
I was like,
So you have an IP prefix, so you can know which NIC to use to send ONOS connections.
that's for inter-cluster
That
communication.
can be different on every node.
Uh,
It was also a property, like a legacy property of Hazelcats, because Hazelcats requires you to be on the same subnet.
yes.
But it's not a requirement.
It's a test time environment variable
I
essentially.
think the I might be not remembering this correctly, but IP prefix is there is no per IP prefix. There is only one IP.
Yeah,
prefix.
it's global. Well,
No, it is,
You
but
could, you
it-
could put it. You could write a different one into every config file
Correct.
that you deploy to each.
yeah.
Ah,
Okay.
Okay, you mean that? Sure. Yes.
And the API for this is going to be the same thing. You just do a put to the cluster.
For the metadata store. Yes.
Yeah.
It's primarily going to be.
For
Well, I
for
think
the-
there will be. I mean, it's not
you are exposing a REST API right now that form cluster calls.
correct.
You're essentially going to backward compatibility like that.
So the initial formation of the cluster could remain the same.
Okay. But after that, you go to the
But then
net
there will
nodes.
be additional ability to add and introduce and get nodes from the cluster.
And if we're using another third-party metadata store, the cluster will just react to changes on that, and we could update that. If we're using Zookeeper or SCP,
Right.
we changed that. The cluster, presumably that plugin is going to be monitored.
Correct. So I think we follow the same pattern. I mean, you'll have like a store
Yep.
implementation, which is backed by Zookeeper
Yep.
or by ONOS, like consistent map. But ultimately, the interaction with the store itself is going to be put and get.
Yes.
But the API that you define might be a slightly higher level than put and get.
So the partition number is fixed. Yeah, we need to configure the fixed number of the
Partitions, yes.
So this fixed number, what's the root cause? Why we need to fix the number? Why we cannot dynamically accumulate? This is theoretical
Reduction in complexity.
complexity.
Well, so you have a mapping from the data keys to partitions, right? And if you change the mapping algorithm, that's a complex operation.
Requires data migration. Well, maybe it does. I don't know.
Well, so there is data migration, and there is also like splitting of partitions, atomic fashion in a running system. I mean, if you can shut down and take some time, then so many things are possible.
But I think you're going to point out there's going to be a certain amount of growth in a cluster size, at which point it no longer makes sense to grow that cluster.
Exactly.
You're going to have just different clusters.
Yeah.
And so coming up with a static partition size makes it not that difficult in those situations. Elastic does the same sort of thing. It basically says set it up for your projected growth.
Yeah, I mean, the thing is, you set a number of logical partitions. There's a bunch of nodes that get put into these partitions, and then they enable you. Like the key here is you want to be able to size the physical hardware up and down, right? And you can do that in a fixed partition set.
And fraction of the cost
Yeah.
in terms of complexity.
And like I said, if we logical growth up to 10 nodes in a cluster, 16 partitions, that's probably good for the lifetime of that.
Yeah, exactly.
But yeah, you can start with 30 if you.
Exactly.
The minimum partition size is 3, right? Yes. So if I fix the number of partitions or something, cluster all the partitions.
Yeah, essentially every node is part of every partition, right?
So the minimum number of partitions you could theoretically have one.
So minimum partitions is exactly. You can have
one partition, but you need 3 members per partition.
Yeah, you need.
Because you need to be able to have the majority.
Sorry, what is that one?
So you could have one partition.
Yeah, one partition.
You need
Number of
a
members.
list of
You need minimum of 3 members per partition.
So if you just have one partition and a 3-node cluster, you add a 4th node. One node will not have anything.
Yeah.
Right. So there is a node balance, node
But
imbalance.
with 3 nodes in a partition, you're dealing with two failures, essentially. You'll have majority until you have the second failure.
Even in a four-node cluster, you can only deal with.
Yes.
Yeah, but
So,
if you increase the number of nodes per partition to 5, say,
Then you
then
get
you
Yes.
can do two failures.
Yeah.
Any two nodes.
Any
Which
two
is
nodes.
added benefit of more.
At the-
And you're supporting that. You're supporting the number of nodes per partition, just not the number of partitions.
The cost though is increased coordination cost.
Absolutely.
You pay for
Nothing's free.
Just to ride on this last topic, I'm just wondering, so there's a huge difference, of course, in practice between being able to tolerate a single point of failure versus being able to tolerate a number of failures, provided you have sufficient redundancy in the system. Of course, it always costs, but sometimes that cost is okay. If you're looking at it in that, like the chord concept, would only really go down to the central office level. So you think about remote places that require lots of truck driving to reach. If we could put the maintenance on a schedule instead of being reactive, so if there is if the system can only tolerate a single point of failure, and you receive a call that you learn that the server is down off the tree, let's say, then you better to go right away to that place because you are now operating on a very thin ice, right? But if the system can tolerate design number of failures, then you can say every Friday we visit that site and we replace whatever went wrong, and that's the huge difference in terms of operational expenses. So my question is that statement that with proper overhead you can tolerate more than one failure, that goes beyond the cluster management, right? It is true for the other coordinated data structures.
Yeah, so all the coordinated data structures are built on top of this partition service, right?
So that says yes.
Correct. And also keep in mind that, you can see that if you take out two nodes in a 5-node cluster, you have actually taken out some partitions, right? So again, at least the recommendation is that you want to have these nodes on different failure domains, different power supplies, and so on, right?
Yes.
So at least the chances of coordinated failure are less. Okay, if that is not acceptable, right? Now there is nothing saying that you can only have 3 nodes in a partition. Okay, you can always say that my partitions will have 5 nodes in it, but I will have fewer number of partitions. You get some, which is you have the ability to not tolerate 2-node failures and still operate the cluster, right? But you are paying additional cost for each operation that you're doing. So sometimes these things are tunable. The default setting sort of works for most use cases. But if you're in a setting where you have to tolerate 2-node failures without any interruption in any services, then you might go with a slightly different configuration.
The other thing to your point, right, is right now we have static partition definitions, right? We statically say this is how many nodes you have in the entire cluster, and this is how many nodes you have per partition. But if you have the ability to migrate nodes into and out of partitions, you detect a single failure. As long as you don't have 2 concurrent failures, then you're okay. If you have a single failure, then you migrate that node out of the partition or leave it there and migrate another node into the partition to maintain.
You mean by concurrent failure, you mean concurrently occurring?
Yeah, meaning a failure that happens in a time span between the time it takes you to react and move someone else.
That's right.
And the data.
So only verified.
So
Versus failure is not faced before. It's not.
Right.
So in that case, you could have a failed node, and you could just move out of the partition and move another node into the partition, and you can continue to operate across your entire key space until Friday when the data guy.
and there's multiple things that are happening to fix a failure here, right? Rather than almost say C goes down, so I now move E into P2 and P1. C goes down, the manager notices that I spin up a new instance of C and add it back in the partition. So we have to decide, we might have competing strategies for trying to recover a failure, but we've got to coordinate that too.
Yes.
But yeah, once you have the ability to migrate people into and out of these fixed partitions, you can grow the size of each partition according to your failure recovery strategy.
And that was my comment about a fully decentralized system where every node makes decisions on its own. Again, this is like today's networking, right? You might eventually converge, but you can actually do a better job if you have like a higher level visibility where you can actually say that I want to do this right now, right? And also, like if you're already using a system where you have Mesos and other like cluster managers, then you just like ONOS can just react to what they say it should do instead of it trying to like deep level.
Right.
Which means ONOS has to start really, really quickly. It's a little bit of a concern about that right now. The speed of ONOS starting up
Has to be fast.
has to be fast.
Right now, it's about 45 seconds from ground up.
On which hardware?
It's about 35 from bare metal. Right?
On fast, what is it? A minute and a half on Raspberry Pi.
Good play. Yeah, it's about a minute and a half.
Okay, almost 15 seconds of that is bringing up all the options. Yeah, I think that we can fix.
Another opportunity for community contribution.
Startup
Someone put him in a box.
All right. Well, I think we reached the end of the meeting. Unless there's any other questions or suggestions or objections.
Thank you very much.
We can call it a day.
Great, thank you.
So thank you. It was a good discussion. Thanks, Madan, for preparing all of this. Bye-bye, everybody.